This is an intro to what rational functions are. So a rational function, it's a quotient of two polynomials. Remember, quotient means fraction. So all I'm saying to you is a rational function, you've got a polynomial in the numerator and a polynomial in the denominator. And then those two expressions that I wrote down are just the most general ways you could write a polynomial down. Maybe some words. Remember, the highest exponent you see in the top is the degree of that polynomial. And this coefficient an out front, call that the leading coefficient. So like the polynomial on the top has degree n, whereas the polynomial in the bottom has degree m, and then bm is its leading coefficient. So let me give you some actual concrete examples of these rational functions. So maybe you take a fraction like 3x squared plus 1, that's a polynomial, sure. Divided by 2x minus 5, that's great, you got a rational function. Now, there's nothing that says that the degree of the top has to be bigger than the degree of the bottom. Doesn't matter, I don't care. So just to give you an example of that, this thing has degree 1, whereas this thing has degree 5 in the bottom. All I care about again though is it's just a fraction of two polynomials. Now, the last one here, what if I just took x squared here? Well, if you think about that, it's the same thing as x squared over 1, and a constant is a perfectly good polynomial. So, polynomials, constants are all examples of this more general thing called rational functions. Just like you're thinking about, integers are really fractions if you think about, well, 1's an okay denominator. All right, so what we're interested in is looking at the graphs of some of these, and they're kind of interesting. And so I'm going to draw you a couple pictures here as examples. So here's a graph of a rational function who I named f here. And so what are some of the key things that I want to kind of highlight with this? Well, it looks like if you're looking along the that's the y-axis there. Looks like that red graph never crosses it, but it looks like it sure gets close to it here, and it sure gets close to it here. And so what we'd call that then, we would call the x-axis in this case a vertical asymptote. So it's this vertical line that the graph wants to get really close to, but it never ever crosses. And so what you also see, right, is that there is no red dot anywhere on that axis, so the function's undefined at a vertical asymptote, and that's the same thing as saying that it never crosses. So to give you another thing that I want to look at here is look at what happens as I go really far to the left. Well, my red graph wants to get really close to the x-axis, and look what happens when I go really, really far to the right. Looks like my red graph wants to get really close to the x-axis again. So this horizontal line, the x-axis, is what's called a horizontal asymptote. So how would I say some of that with my math words? When I write something like this, x arrow minus infinity, that just means we're going really far to the left. Similarly, when I write something like x arrow infinity, that just means that we're going really far to the right. So again, what we see is that when we go really far to the left or to the right, the y values, the graph, right, gets really close to 0. So the the x-axis, whose equation is y equals 0, is a horizontal asymptote. So I've got this concept of asymptotes that I didn't see before when I was graphing like parabolas and stuff like that. I'm going to give you one more example. It is something like this. So the function is in red, but I've got this blue line here that, again, somehow the function wants to get close to, as how we should look at this again. As x goes really far to the right, the red gets closer and closer to the blue is what I'm trying to say. Or as you take x values really far to the left, again, the red starts to get closer and closer to the blue. So this line here, acts as something that's kind of attracting that red function. So we'd call that a slant asymptote. So what we're interested in is, okay, given the equation of f, how do I find some of these things, like the slant asymptote if it has one? Or given the equation of f up here, how do I figure out from the equation if it has a vertical asymptote or a horizontal asymptote? And so to do that, I want to maybe write down what are some of the key things we're looking for in order to maybe try to graph one of these just from the equation itself. So if you're given the equation, what are the things that you want to be able to identify? You want to be able to find the zeros, the x-intercepts in other words. You want to be able to find the y-intercept. You want to be able to find the vertical asymptotes. And remember, the graph never crosses a vertical asymptote. It's undefined there. You want to be able to find horizontal asymptotes, which I'll call HA for short. It's okay if the graph crosses a horizontal asymptote. Horizontal asymptotes, again, just care about what happens when you're really far to the right or really far to the left. So it would be okay if this red graph started like bouncing back and forth along that line, as long as it gets closer and closer to it as I go to the right, say. And then back down to here. The last thing you might want to find is the slant asymptotes, and then maybe there's secretly a number 6 here. plot additional points as necessary. So in the next few videos, we'll do some concrete examples working through these.